This is working? Yep. Thank you very much. Thank you for inviting me. It's a pleasure to speak here today. I'm not going to speak about post-quantum at all, but two completely different topics in my presentation. The title of this presentation is The Future of Hardware Security is in Open Standards. And I picked two examples of work that we've been doing at Rambus, but that also led into standardization work, which hopefully will convince you that there's something good about open standards and that this should be the way to go in the future. Okay, so let's see if I know how to... Okay, so part one is about differential power analysis and the so-called test vector leakage assessment methodology. If you've been here for the trainings, I believe Leila Bettina gave an intro to side channel attacks, which was probably way deeper than this, so this will be very high level. But my goal is to talk a little bit about standards as compared to, I guess, her technical intro. So, all right, side channel analysis. What is it? Well, it was discovered at CRI. CRI is the former name of Rambus, or should I say Rambus bought CRI, so it's now the same company. In the mid-90s by Paul Kocher. It's a very low-cost, non-invasive attack on crypto hardware. So it allows you to do different things. Amongst others, the most fun part is key extraction, obviously. But it can also allow you to do reverse engineering, find, for example, what secret S-boxes are out of specific algorithms, all sorts of fun like that. Pretty much all cryptographic algorithms are vulnerable. Mostly the easiest ones are actually the public key algorithms, RSA, Diffie-Hellman, and so on. But also the symmetric key crypto, you can break it with differential power analysis as compared to simple power analysis, and I'll explain the difference between the two. And also then the MAC algorithms such as HMAC, you can also extract keys, but it does get more and more complicated as you move along. All types of hardware and software are affected, all types of implementations, even if you have a lot of noise, it will still work. You need more power traces to be able to do it, but it still works. And you can do similar techniques with different signal sources. So you can use power measurements, but you can also use electromagnetic measurements. It still works. Okay, so a little bit of intro. This is supposed to be very simple. So simple power analysis, how does this work? Well, imagine you're doing an RSA computation. RSA typically when you implement it, it will be implemented as a very straightforward exponentiation algorithm. So there's something called a square and multiply algorithm. And since this is a modular exponentiation, you need to know that the secret is the actual exponent, and this exponent has some bits, and you want to find out what these are. So your square and multiply algorithm will perform very easily. It will say if, the bit of your secret exponent you're currently working on is equal to 1, you perform an extra multiply on top of a square every time. Okay, super simple. So what that means, though, is that you can very simply read from a power trace of your execution what the secret bits are. So you can see in the picture here, there's, small peaks and high peaks. Whenever there's a high peak which looks different, this is most likely a multiply. It's a little bit different from a squaring. And so the smaller peaks are all squares, and every time you have a square followed by a multiply, now suddenly you know the bit is 1. So look at the trace and just read out the secret exponent. All right, pretty cool. Sorry. Okay, so that was simple power analysis. That means you need one trace, essentially. Look at the trace, find the secret exponent of your algorithm, and you're all done. With symmetric algorithms, it's a little bit more complicated. It's a differential style attack, which means that you need more than one trace. You have to combine traces statistically and try to figure out the secret information from that. All right, so let's look at what this works. If you look at one power trace here, let's say it's an AES, for example, an AES execution. One power trace, the signal to noise ratio may be very small, so you don't actually see much. But statistically, there's influence in what is going on. So let's say, for example, you look at a specific bit in a specific register. It happens to be that whenever this bit is either 0 or 1, the power consumption, what's happening will be slightly different. So if you look at it straight, like that, you don't see it. But if you now take a lot of different traces and combine them, statistically you will see a difference in where the center of the signal amplitude is located. So in this graph here, the red graph shows you what happens when the bit is 1, and the blue one kind of represents what happens when the bit is 0. I think it's the opposite, sorry. Anyway, there's a difference, and if you have enough traces, you will see the difference. Okay, so now how does DPA differential power analysis actually work? Well, you use statistical methods to analyze those differences, and then you can extract keys and data out of that. You can do the same thing with electromagnetic measurements. It will work just the same way. So different sources are possible. And now we can have a look at how this actually works. So still very simple examples. Okay, so let's walk through an example here. Let's say you have an AES implementation. The first part of the implementation is typically you take a key, you XOR it with your input data, and then you run through a bunch of S boxes. Now, if we look at that key, we take the first 8 bits that will go through the first S box. When you XOR it with the key and run through the S box, you're applying a nonlinear operation, and we're trying to find out what's happening at the output of that first S box. So we're going to look at a selection function, for example, the least significant bit of that output, and try to figure out what's happening there. So the principle is that you're going to try to guess what the first byte of that key might be. And then you're going to try to do some statistical analysis on the power traces that you're collecting to figure out which one is your right guess and which ones are wrong. 1 out of 256 will be correct, and the other 255 ones will be wrong. Okay, so how do you tell the difference? Well, very simple. Let's say you have a key hypothesis of 8 bits here, so the possible value is presented in green because we happen to know it's the right guess, so you can see what it looks like. With that key value, you can add it to the input data that you chose, and you can predict what the value will be at the output of the S box. So you know exactly what the output will be once you've guessed the key, let's say. So what you can now do is you can take all your power traces from different input data sets, and you can sort them according to whether that predicted output bit of the first S box is 0 or 1. Okay, so you sort them, put them in 2 buckets. The left-hand buckets is traces with a predicted least significant bit of 1. And the right side here is traces with predicted least significant bit equals to 0. Okay, so now you have a bunch of traces in each bucket. You take all of these traces in each bucket, you average them, so that you have kind of one global representative trace, and then you subtract those 2 averages. Now what's going to happen is, if your key guess is correct, typically you will be right about all the 1s being processed in that one bucket and all the 0s being processed in the other bucket. So you should see some statistical difference in the means, in the averages of these traces. And so in case of a correct key, what happens is this kind of power trace as a result. You have a bunch of, noise, and then suddenly you have some peaks in there. This means, okay, in this particular place, my guess was correct, and so I have a chance that my key byte that I've been guessing was correct too. Sorry. No, I'm good. Thank you. Okay, so let's see what happens if the key guess is incorrect, because it's too easy to just say, okay, if I guess correctly, I will see it, but there has to be a difference with when I guess incorrectly, otherwise I don't see anything. Alright, so when I do guess incorrectly, what happens? Well, essentially what I'm doing is completely random predictions, right? I'm trying to sort traces into 2 buckets according to a wrong hypothesis. And so eventually I'll have about half the traces in one bucket represent a 1, the other half is 0, and same in the other bucket. And therefore, if I do the same exercise again, average the traces in both buckets, subtract, well, I end up seeing nothing, because now I'm just randomly sorting stuff and they all look alike on average. And so the difference between the correct guess and the incorrect guess is very easy to see, because the correct guess, there's not really a lot of mathematics involved. You just have to look at the power trace, average, subtract, look at the power trace. If you see peaks, your guess is correct. If you don't see peaks, your guess is not correct. So you can filter out all of the incorrect ones and figure out the one byte that you were looking for. Okay, and then since this is a yes, one S box with 8 key bits, now you iterate through the 16 S boxes, do the exercise again, and recover the 16 bytes of the key. Super simple. Okay, this is very high level, but just so everybody can understand how this works. All right, so now what do we do to try to protect against this? Well, so in typical power analysis countermeasure world, you have a different number of things that you can do. You can try to, for example, obfuscate a little bit what you're doing. You can try to reduce how much the hardware actually leaks. You can implement so-called balanced hardware or software and dynamic differential logic. So you have essentially, let's say, 2 rails that will do the opposite to each other, so that it compensates every time you send a signal through them. And then, so that's kind of at the design level on the left-hand side. And then on the right-hand side, what you see is when you try to add noise or make things look more random so that you can't tell statistically anymore. So you can add amplitude and temporal noise, for example. So you try to shift things in time to make sure that the attacker can't align the traces correctly, because then again you're sorting completely random stuff. You can try to add amplitude noise. You can try to use dummy operations, for example, for time shifting. And then the more theoretical mathematical ways of doing it is to incorporate randomness. So now what you're doing is that you're taking your original data, you're masking it with a random value so that it has nothing to do with the data anymore that you were supposed to be processing. You run through the algorithm, do some tricks to realign in the end, unmask in the end, and provide the output. But throughout the computation, whatever you were supposed to be doing is now looking completely random. And so it's way more difficult to try to sort. Then you have to go to second orders, third orders, higher orders in order to be able to attack this. Masking for symmetric key crypto, it's called blinding for asymmetric key crypto. You can use something more evolved, such as threshold implementations, where you start sharing each value and variable you're dealing with into several parts, not just 2 for first, second order protection, but many more. You could have n shares, and then you know that whenever you try to run statistics on n-1 shares, you can still not see anything. That's provably true. Okay, and then there's one other technique which is called protocol level countermeasures, which I can explain a little bit, which is in a setting where you're deciding you can't really change the hardware too much. Everything I talked about previously is either a hardware change or a software change, but an implementation change. Sometimes you're in a setting, a configuration where you cannot actually change the implementation, and then you have to come up with something that will allow you to provably show that there is not enough information in what you're doing and in the number of times you use the correct key, that you could do statistical analysis on it. So for example, one way of doing this is to use a tree of keys. Instead of using always the same key, you can derive different keys from your first key and walk down a tree and make sure that each one of those keys that you're using in the tree only gets used a few times and not enough for an attacker to run statistics and statistical analysis on the traces. So for example, in a challenge response mechanism, what you would do is use the challenge bits one by one to run down your tree. Together, in order to go from your root key to all of the leave keys, what you do is you apply a one-way hash function. So you run forward with your key by one step for each bit of the challenge. That gives you one of 2 keys. So for example, the red part here will show you the path that you will be using for a specific challenge, following the bits. And so what you can prove in this case, if you can't change the implementations and do anything on that side, what you can still prove though is that each one of the keys that you're going to use in your protocol only gets applied to 3 different values at the maximum. There's one value that leads from the root to that key, and then from that key on you can go one of 2 ways, depending if the bit is 0 or 1. But each one of these keys will only be used for 3 different inputs, and you can show that for 3 different inputs is not enough to run statistical analysis on anything. So your keys are safe. Okay, so this is another way of doing DPA countermeasures. So now you have kind of a little bit of a global overview of how to do this. Great, we're almost done. One thing remains though. How do you prove that any of this works? Okay, so this is the part where I'm tying it into standards. Since the late 90s, side channel analysis has been studied extensively, and many people have written papers, done attacks, corrected them, added countermeasures, re-attacked them, and so on. A lot of research has been done, but how do you test this implementation? How do you do as a certification lab, for example, as a authority that decides whether your implementation is good enough or not? How do you do that? So what we're lacking, or have been lacking for a long time, is formal testing standards and formal testing criteria. In common criteria, for example, most of the cases you rely on the expertise of the testing lab. So the testing lab will have experts. You give them your chip design, you give them your implementation, and they will spend a month or 2 or some amount of time trying to break it. In the US, for example, it's very different. Labs don't typically have all of that kind of expertise and don't necessarily want to build it up at the start. So what they're looking for is a way which is more of a checkbox-like testing. So it means, okay, run these tests. If they all pass, like, the FIPS random number generator test, for example, if all of that passes with these specific test vectors, then your implementation is secure. How do you do that for side channel analysis? That's a very tough question. It's not easy to do at all. So for the longest time, this has been a problem, an issue, because we didn't have good side channel protection requirements in the standards. It didn't say you have to do A, B, C, D, E, you're good, right? Because it's hard to do. So there was then waivers for everybody to say, okay, we know it's a problem, we know it's an attack, but we'll waive everybody from having to deal with it because nobody knows how to test it really in a checkbox manner. So what you do is you end up having a chicken and egg problem here, because you can't write requirements because you don't know what they're supposed to be, and then the labs don't want to deal with it because they don't know how to test it. So they won't move until they have requirements, and you can't do requirements until you have a testing methodology. All right. So what you need is some kind of objective, measurable, reproducible test for each algorithm, because every algorithm is different. You need the tests to be efficient and low cost. They should not require exceptionally skilled testers. So it's not about the capabilities of the experts in the labs. It's about tests that you can apply automatically. That's the question. How do you do that? So you could perform them at the designer level, which means that you can know upfront that your implementation is hopefully secure. You should have tests with good coverage and results that indicate to you that you've achieved a good level of resistance. You should also have tests that could tell you when you don't pass what went wrong. What exactly is the problem? And then what you want to do is that you want to make sure you document everything correctly so that both the designers and the labs will know what the problem was and what the result means. Okay. Sorry. I hope you're all awake now. Okay, so the focus is on information leakage and not on key extraction. So what we've come up with in the past years is something that is called the test vector leakage assessment methodology. So the idea here is to use a specific statistic in a Welch's t-test to perform a difference of means significance tests. So we want to make sure we try a statistical analysis on one set of data, and then we compare it to another set of data, and this allows us to say whether your distributions and whether the behavior of the set that you're looking at looks random or not. So you compare two sets of traces, usually one with a fixed input value and one with random input values, and if those sets don't look too different, you know that you're pretty close to random behavior, kind of in a nutshell. So this is what we've been working on. You need to make sure that you target very specific sensitive intermediates so that the result of your tests means something. And so you can show running these tests that if you don't have any statistical significant difference, that what's happening inside of your execution in your implementation should not leak. Okay, so you perform tests twice on two independent data sets, and that gives you a very high confidence of succeeding. All right, so I just mentioned it before. This method is called test vector leakage assessment. It doesn't have a pass-fail criteria, so the device fails if your Welch t statistic exceeds 4.5 sigma for two independent data sets. For a large set, a single excursion also implies 5/9 confidence, so 99.999% confidence. When the test is repeated, the probability of excursion occurring randomly at a certain point in time is also negligible. So this is when you repeat it twice, but also if you have very large data sets, you can actually avoid repeating it twice. It compensates for large trace sizes and large number of tests. Okay, so now what happened with this? Now we have defined a testing methodology. We think we know how to build countermeasures. We know what the problem is. How do we go about standardizing all this? All right, so this has started a few years ago. There's a few different ISO specifications that start dealing with this. The first relevant one is 19790 about cryptographic modules and how to protect them. And then there's a few others, and I'll go into a little bit of detail in the next few slides. The question is, how do you make sure to write into those documents and to standardize a way of testing that everybody could use? So this is what we're trying to answer here. So the first one, ISO 19790, 2012, I don't believe it has been reviewed again this year, but I don't believe the text has changed much. So it has the following content. It is about security requirements for cryptographic modules, and it defines 4 security levels. In one section, it talks about non-invasive security, so we're getting closer to side channel. So this is SPA, DPA, timing attacks, and all of these things. And it specifies modules may implement various techniques to mitigate against these attacks. And then in terms of non-invasive attack mitigation techniques, it says the ones that are not referenced in Annex F will be validated when requirements and associated tests are developed. The ones that are referenced in Annex F shall meet the following requirements, and then there's requirements for level 3, strong, and 4, stronger. And it says it shall be tested to meet the approved non-invasive attack mitigation test metrics referenced in Annex F. Now, Annex F is not all that filled in yet. It's still a bit sparse, so the link is kind of still missing a bit, but we're getting there. So pieces of the puzzle are starting to fall in place. You have all the requirements, all the shells and everything. There's just one little link missing. But we're very hopeful. Okay, the next one, 17825 from 2016. So this one does actually talk about testing methods for the mitigation of non-invasive attack classes, side channel attacks. Non-invasive attack mitigation test metrics for levels 3 and levels 4. Remember, 3 is strong and 4 is stronger. It talks about side channels such as power, electromagnetic, timing attacks, In the future, there might be room for photon emissions, acoustic attacks, and things like that. And it talks about the two following things. So you want to collect and analyze measurements, and it gives you certain test limitations. And typically, the test limitations are defined in terms of how long the test might take and how many waveforms you're allowed to use. So level 3, which is strong, has 6 hours maximum per test, 72 hours max total acquisition time, and 10,000 waveforms. And stronger, you have to resist to 24 hours max test time, 288 max total time, and 100,000 waveforms. So now you can see how the pieces of the puzzle start falling into place. You just have to link this one, 19790, to this one. So bear with me. Soon. All right, 2 more of these still under development. How do you now define requirements for your test tools? Because you have to measure things some way, and you also need to define test tool calibration methods. How do you calibrate all these things such that they will allow you to run the test that will show that your implementation is secure? Still being worked on, 20085, Part 1 and Part 2. Test tools and techniques for Part 1 and calibration methods for Part 2. Under development, but all of the pieces are there. We just need a little bit more work. Okay. So there's a couple other areas where such tests and such requirements start getting mentioned. For example, in the content protection area, an organization called Movie Labs has put out new specifications to protect enhanced 4K and above HDR style movies and things like that. So the high value content that studios put out. And they also list a requirement to say the resistance shall be established through testing, through statistical analysis of test signals for leakage. It's not very precise, but it's getting there. All right. So in terms of side channel attacks and testing and standards, what we're trying to do, and hopefully getting closer, is to find a high quality, efficient, and cost-effective testing methodology where operators need modest skills in the area, so you can go checkbox-like. Testing can be performed by designers. You can get quick feedback from it. And therefore, what we recommend, and what I think the world is starting to move towards, is the TVLA methodology. Test vectors are designed by side channel experts, so you can know how to focus on the exact internal sensitive areas that you should be looking at. You focus on measuring leakage instead of trying to break the key out, because if it doesn't leak, it sounds better as an analysis than being able to just break a key out of one implementation, so to speak. If you're on a boat, you'd rather be on a boat that's not leaking for sure, rather than one that you will see sink at times, right? I'd rather though that it doesn't leak, so I know I'm not going to sink, kind of. Okay, don't quote me on that one. Sorry. Okay, and then standardized statistical scoring with objective pass-fail criteria. All right, so ongoing next steps. Standardization efforts are continuing. Those ISO specs are getting to a close. That's perfect, great. And on the FIPS side of the world, the 140-3, which is currently still unpublished, is most likely coming out soon and is most likely going to align with the ISO spec. That's why I'm talking about it as well. We've been waiting for FIPS 140-3 for quite a while, and it should normally converge with ISO 19790. All right, so far so good. This is all about side channel attacks, standardization efforts. I hope I convinced you somewhat that it's great to have open standards that can help you test your implementations and be secure. So let me, maybe in the second half of this hour, move to a slightly different topic. Okay, part 2. Completely different topic, somewhat related to side channels as well, but different topic. RISC-V based hardware root of trust. Again, I'm going to try to show some work that we've done at Rambus to try to implement a secure hardware root of trust. and then tie it to open standards in the form of a discussion on RISC-V and why that's good for everybody to try to implement around open source processors, open source specifications. Okay, so we've seen in this is a link into side channels a little bit if you want, but we've seen in the beginning of this year some publications on new attacks on processors called Spectre, Meltdown, and more recently in August called Foreshadow. What this shows is that there are vulnerabilities in all the major processors out there, including from Intel, AMD, some ARM CPUs, and that there is room for more attacks on these objects and room for way more results coming out in the next few months and years. People didn't typically look at processors in that way before, but it turns out that when you want to optimize for performance, if you want to go really fast, you do a lot of things that you shouldn't be doing from a security perspective, meaning you speculate on what the results might be, you take different branches you shouldn't be taking, you come back with results that you should not be leaking to anyone just for performance reasons. So how you deal with this is really a big open question. There's some patches around, there's some things that can be done to mitigate Meltdown, for example, but the other two, Spectre and Foreshadow, look a little more tricky. And there's no complete path to a solution right now. So this is also a call for the community to think and try to come up with creative solutions. Okay, so all three of these vulnerabilities take advantage of CPU performance enhancements. Speculative is one, out of order is the other one. No matter how you do it, if you work with data that you're not supposed to look at, you're not supposed to see, and you're not supposed to bring back to the cache, you're leaking information at some point. All right, so citation from Mike Hamburg. This design approach will go a long way in helping to prevent vulnerabilities if you can make a separate design between your sensitive operations and everything else you're trying to do at a super high performance. Keep things separate is kind of the message. If you keep it simple, put your sensitive stuff in one slightly more secure place, then you might be fine. Okay, so let me tell you a little bit about the trial implementation here, or the work that we've been performing at the company to build something like that. A small, secure processor that will hopefully allow to run sensitive operations, including crypto operations, including keeping your keys safe and all of that on a slightly separate processor. So you have your general processor processing going on one side, and you have secure processing kept to a smaller smaller security boundary. Okay, so what do you have in there? You have a few things in there. You have inside your secure boundary, you have a custom RISC-V CPU. That's why I'm mentioning this, so I'll come back to RISC-V a little bit later. You have a part of secure memory, which means you have your own SRAM to compute in. You have your own dedicated non-volatile and OTP. And you have crypto acceleration, AES, SHA, public key acceleration engines, and so on. So what you use this for is the secure functionality you want to get out of it is for secure boot, remote attestation, such as for TPNs, for example, authentication, runtime integrity, and you can run many different security applications inside this smaller boundary and keep all the rest of your stuff that you're doing for high performance that doesn't require security on the general processing side of the world. Okay, so a few use cases here, what you can support with this. You can put your data in a safe place because you have keys and everything available to encrypt it and then to put it in a bigger area where it's not at risk because it can't be decrypted or anything. You have secure key storage. You can use you can personalize your device to make sure that you can trace who is authorized to use it, who does it belong to, who's the owner, when does it go from one owner to the next owner, how do you transfer rights. You can do key and data provisioning, use it for authentication and attestation, and you can see on the right-hand side there's a whole column of other things you can do with it. You can securely update firmware. You can load applications into it for running securely. You have specific features in there so that your debug functions are secure as well. And you can use it for configuration management. This list is too long. Okay, so a little bit of terminology before we dive into some of the details. We have two things in there that we, for some reason, called roots and containers, and in other worlds this means something completely different. But in our world it means a root is an entity that's composed of an ID and a specific permission set for access to the root of trust assets. So you have assets in there, you have permissions on who can access what and how and why. And the root defines, it's kind of the origin of everything, and it defines the security context in which user applications can execute. So when you try to load an application, the root will be there to tell you, oh, okay, you've been authorized by this root, and so you have access to these specific assets, and you have these specific permissions, and you can do these specific things, and nothing else. Okay, and a container is the software that you load, application that you load into this secure boundary, secure execution environment, if you want. User privilege applications that run with specific rights, specific access to specific assets, and controlled by root as defined above. Okay, so root and containers. Somebody's from the software world, there's completely different definitions for that, so keep those in mind just for this talk. All right, so how does this work? You have a CPU, you have a memory protection unit, and a central processing unit. We took the approach to base it on RISC-V because RISC-V is an open instruction set architecture. It's published openly. You can download the specs from the Foundation's website, and if you implement this instruction set, you're actually compliant with other implementations out there that are trying to work off of the same instruction set. And so this gives you an ecosystem in which you can play. It does support 3 privilege levels. You have machine mode, supervisor, and user mode. So all these 3 different privilege levels have different privileges. Obviously, machine mode being the most secure part, down at the hardware, supervisor mode above, and the user mode is applications that you can load on top. And then the MPU sets regions of memory for access by one or more of these privileged modes. And the access type that goes with it, and you can lock these registers until the next reset. So whenever you're running, those privileges and access rights are defined and set, and for the time in between 2 resets. Okay, then what else do we have in here? We have some OTP, so one-time programmable memory, which is non-volatile, and this can store different things. Amongst others, what we store in here is the device ID, so that every device is clearly identified. You know which one it is. It has lifecycle state bits, so it tells you which part of the life cycle am I in. Am I just being manufactured? Have I been configured with a root? Have I been passed on to the next owner after the root? Where am I at? Am I at the end of my life cycle, and am I coming back to the factory for debug? For analysis, so you can configure all these lifecycle bits. And it also has a device unique key. So this is kind of a little key that you start off from and derive all the other keys from. It has a table of root IDs and permissions. So that's the part that's stored in OTP. So each root has a set of specific permissions associated to it. It's a multi-root device. And all of the permissions are usually at the highest level, and then you downgrade after that. So the root has the highest privileges, and then whenever you delegate permissions to someone else after root, those permissions have to be a subset that is smaller, equal or smaller to the ones that the root had originally. It has general purpose NVM, so you can add more information to OTP afterwards. That will allow you to restrict those permissions for different user applications and different users that come after the root. And the OTP permissions are enforced in hardware by the OTP management core. All right, so that's the OTP. We've seen the CPU, the MPU, the OTP. Next one is crypto cores. All right, so for every hardware root of trust style of device, obviously you need some crypto to be able to enforce things, but also to run specific functionality. If you're talking secure boot, if you're talking authentication, you're talking encryption, all of that, you need crypto engines. So we have a number of different cores in here. We have obviously an AES engine, a hash core, a public key engine, so you can run public key cryptography, accelerate your math operations in a large integer world, and all of that. So you can read here on this slide kind of which subset of crypto we've thrown in here so that you can do everything that's required, but not overloading the entire design. Okay. We have a key derivation core. What this one does is, remember, you have a device unique key in the device to start with. And then from there, essentially for sound key separation purposes, you want to not be using a key for two different purposes. So you will be able to derive new keys with one-way hash functions going forward in a NIST-compliant way for every single different reason you might want to use a key for. So never use keys for two different reasons. Always try to derive a new key that will allow you to use for different purpose. So if that one by some kind of issue gets hacked, maybe you can't go back to the original keys, and every different application or reason for using will have its own specific key. The key derivation core operates independently of the CPU, so this is completely done in hardware, and can also deliver keys outside the hardware core if you want to do so. You plug that directly into hardware, and then you can deliver keys elsewhere if needed. Okay, other important cores in here. The key transport core, I just mentioned it. You can output keys on certain outputs if you so wish, but you have to be very careful about how you do that, and you have to connect it directly in hardware to other portions that you're sure you want those keys to be able to go to. A NIST-compliant TRNG and a DRBG as well, and a DMA for faster memory movements. All right, this was kind of the hardware part of the architecture. Now what comes on top of that is a software stack that allows you to do many different things, including being divided into 3 privilege levels. So this is where we tie back into RISC-V as well. So at the lowest level, at the hardware level down there, is the machine mode, which runs all the security sensitive code, internal secure boot, for example. One level above is the supervisor mode. So here we're talking about operating system, Zephyr, for instance, and some hardware drivers, and yet one level above that is the container level. So at the user level, if you want to run an application, this is where you will be located. Okay, so bottom level, first stage bootloader comes out of ROM. It begins the secure boot for the root of trust. It's a chain of trust with signature verification built from ROM through images and OTP and flash. So what you do is you come out of ROM, you specifically configure things specific to this device in the OTP, and then all the signature verification is done on the flash parts once you start loading code out of flash to continue booting up. There's a subset of device drivers included with the bootloader as well. It's platform specific. So the ROM, is device and chip style specific, but the platform specific behavior is the part that you program into OTP. So permissions and things like that is where the difference will be, and this is all programmed into OTP so that it's manageable from a manufacturing standpoint. And then you load signed OS and kernel from flash. The security monitor is also down at the machine level. So the most security sensitive code is stored in trusted flash. It gets loaded into the secure boundary at boot process, and then you can move on from there. So when a container, which is up there at the user level, is loaded, the security monitor is going to verify who owns this. It's going to verify if the digital signature has been computed correctly and you're allowed to run. It's going to verify what permissions are associated to the container and then restrict the access to specific assets. By assets, you mean keys, you mean specific memory regions, you mean things like that. So every time you load an application, you load a container, you end up running in an environment which allows you to do exactly what you should be doing and nothing more. And this is applied at the hardware level, so hardware permissions are applied at that level. Okay, one level up, supervisor, OS kernel mode. We took a version of Zephyr and we modified it a little bit so that it supports application loading, kernel user memory separation so that everybody knows where they're running and where they can't run, and so on. It does provide container access to the hardware cores, so you can run at that level, have access to specific cores down there, but under very restricted settings and under certain configurations only. And it does provide a first line of permission enforcement, including some software-only permissions. And finally, the containers at the highest level. So these are user level developed applications. Each container is signed, as we said, with a specific private key that's associated to the root that's in the device. So you can load it, verify the signature, and have the container execute. Each container has permissions that control access to keys and hardware resources. The permissions are limited by those that the root had in the first place. So a container, as I said, can only have same or less permissions than the root that it's associated to. Sorry. And if Gilles is sitting in the audience, he will be happy to know that the libraries include a C runtime and global platform TE compliant crypto library. Okay, let me see. Quick time check. 51. Let me skip over the building and executing containers. Essentially, in a nutshell, the containers get signed with keys stored in an HSM, and then that file gets loaded and the signature verified, and then you can run. Okay. So let me now tie this back into standards in my last few minutes. Why Zephyr? Well, Zephyr is an existing RISC-V port. It's a Linux Foundation project, which means that it's open. Everybody can have access to, everybody can see it, look at it, review it, and have its own implementation of it. It's a large ecosystem. There's a number of contributors. It has everything you need to develop and to make sure that whatever you're developing runs correctly and so on. Community guidelines, contribution reviews. So we thought this is a really nice operating system that we could be using. We'll transform it a little bit so it does fit our specific root of trust needs. But since it's open, it will fit perfectly. And we can also provide back some information on how it was useful to us and how it could evolve. So all the root of trust software is built using Zephyr build systems, bootloaders, security monitors, OS kernel, and containers. These are all very well-known principles in there, and this is why we picked Zephyr. There's a few others around, but this was the one that fit our purpose the best. And finally, let me tie this back to another open standard, which is RISC-V. RISC-V, why RISC-V? Well, you may have noted that all of the different more recent, I'm going to say so-called side channel attacks, Spectre, Meltdown, and Foreshadow, and so on, all apply mostly on proprietary designs. So people don't publish their designs. You go for performance, and in the end, you end up being in trouble because there's so much leakage in your implementation, so many security issues that you don't even know where to start, how to fix it. So we made a different choice. We said, okay, let's use an open spec, an open standard. Let's use RISC-V. The instruction set is published. Everybody can see it. Everybody can download and implement it. There's extensions to it that you can come up with, so it's flexible enough for you to add what you need into the design. So why don't we pick that one? Okay, so let me then for a minute or two do a little bit of publicity around RISC-V here. RISC-V is a foundation that's controlled by its members. It has a lot of members already. And what they want to do in this foundation is to drive forward the adoption and implementation of the free and open RISC-V instruction set architecture. Notice the words free and open. Okay, it was authored by one of the 2017 Turing Award winners, David Patterson. He and John Hennessy have been working on computer architecture for probably more than 30 years. And they finally decided, okay, David said, I'm going to write this up and I'm going to publish this spec and this is going to be great. So they published an instruction set architecture and a draft privilege spec in terms of machine mode, supervisor modes, and all of that. And they have now realized since January that it might be a good idea to have a little bit of security community having a look at that because of all the problems with side channel attacks. So I have the pleasure of chairing their very new security standing committee, which has already about 30 members. So what we're trying to do is a little bit like we did in our own designs within the company, is come up with ideas of what would be the best way to try to mitigate all these these new style of side channel attacks. Now, obviously, this is a very complicated task, and it's not going to be solved overnight. But the question is really, what can we build into the specification at the specification level, not one level down, because that's usually, companies do whatever they want at the implementation level. But at the spec level, what can we build in? What hooks can we add? What are the things that we can do so that all of these newer style side channel attacks could be mitigated? Very big open question, but we're just starting with this. So what we've done so far is that we've created 2 subgroups, one for cryptographic extensions for this instruction set architecture being worked on right now. So we're dealing with how do we perform efficient AES, RSA, SHA, and all of that by adding instructions in there that help. And there's also a proposed approach to trusted execution environments. So what do we need to add at the spec level to make sure that we can build up these types of trusted execution environments? There's ongoing collaborative work with the RISC-V privileged architecture, so we can try to influence that part of the spec to add more features into there as well. And look at what vector extensions we could be coming up with. All right, so what I'm trying to say here on top of presenting our kind of own approach in the company to build a secure hardware root of trust is that this is the right time for the security community to come together with the processor community. Look at what the problems are, look at how we can try to fix them, and build something into the spec so that we can solve these things at a more general level. Okay, so if you have time, you don't know what to do of your days, then please join us in the foundation. There's a lot of work to do. I'm not saying I do have any of the answers. I have a lot of questions myself. But hey, this is where we start, right? Okay, and you can read all of the press releases and stuff about RISC-V on the internet. Please join us, please come help, and this is the end of my second part of the talk. I hope you enjoyed it. I've walked through a different number of topics, trying to relate them to standards, trying to convince you that open standards is the way to go. And if you have any questions, I'd be happy to answer them. Thank you.
Hi. Thanks for your talk. Very informative. Regarding the first part with the standardizations, so I like the idea of open standards. But as a practitioner in a certification laboratory, I have a fear that once the standards are published and done, they already will be outdated. Because you showed us that some specifics about 100,000 traces, this and this many hours of testing. And in the spec, this was already the highest level, if I understood correctly. Well, from our daily work, I can say that this is our low. This is where we start. So I fear that the standards will be outdated very fast. So how fast can such a standard be updated?
So that's a very good question. Let me try to answer in two different ways. The first thing, I think you have to make a difference between the number of waveforms called in the standard is really for making sure there's no leakage at that amount of waveforms. So you can easily add a factor, I'd say 10 at least, before you start talking about key extraction. So when you start seeing leakage, there's still a margin before you can actually do something with it. So something that might pass 100,000 waveforms will also pass your 1 million waveform test, because at that point you still can't extract keys, so it would still pass. So there's an order of magnitude difference. That's the difference between, a non-leaking boat versus a boat that you can start seeing sinking. There is a gap between the two, and you want to be on the safer side. So that's why I believe they have, in that specific spec, kind of tuned down the number of waveforms. But you're right, things evolve, and every day you can find new ways of being smarter and getting there faster. So what you should do, and I don't have the answer as to how fast it might be to add levels, but you should be adding levels as you go, right? Or you should be revising the specs as you go, have revisions to it, and then say, okay, 10,000, 100,000 was true yesterday. Next year we should move, or in 2 years or 5 years, we should move to 100,000 and 1 million maybe. You should be able to add levels so that each sector and application area can decide the level that's good for me is this one, and there should be tests associated to that.
Okay. Yep. In the first part, you talked about side channel analysis, and then in the second part, you showed a secure processor that looks like it's going to be very prone to side channel analysis. Would you like to comment on the seeming opposition of the two parts that you talked about?
Yep, absolutely. So the design I showed has pluggable crypto cores. And so you can decide as a user if you would like to be resistant to, for example, DPA-style side channel attacks. And so you can choose to plug in DPA-resistant cores if you would so wish. So that addresses that part. The other part, the more Spectre and Meltdown and all of that oriented side channels, are very different styles of side channels. And then in this case, it's more about trying to subvert things that you shouldn't be doing in your execution, even though you are doing them for faster performance, right? So speculative execution, out of order execution, just trying to go faster and predict what's going to happen so you can go faster. In the design I've showed, we're doing none of that. We don't have speculative execution. We are very, sequentially oriented people trying to not speculate at all, trying to keep it safe, which is why this is a smaller security boundary. You don't want to be doing, 4K HDR content decryption in there. This is probably not going to fly. But so it is restricted on that side. You can't do speculative execution. There's no out of order. There are no caches in there either. So all of these things are also addressed in that way. But these are two different reasons why one and the other will not be a problem here.
Hi.
Hi.
This is regarding the crypto modules.
Mm-hmm.
So for every crypto modules, the FIP certificate is must and should. So, FIP certified.
Yeah.
So for module. So basically, FIPS means everyone will be looking at a level 3 as it was suggesting it's a strong, and level 4 is a stronger.
Mm-hmm.
So TPM from an best known famous automotive supplier, currently their physical security is level 3, EMI EMC is also level 3. But overall they claim it's a level 2 certified.
Okay, so sorry, what's the question?
Yeah, so that level 2 certified is also secured enough?
I'm not sure I understand the question. Can you try to reformulate it?
Yeah. When you consider a TPM, the security, the whatever you call a physical security, it's a level 3 certified.
Yeah.
EMI EMC is also level 3 certified.
Okay.
But the overall, the level certified, it's a level 2.
Okay, so the design I've shown here, for example, this is IP. This is not a chip. We don't build chips. So if you want to go for the highest security level for the cryptographic module, then what I've shown here, for example, might not be enough. And the FIP certifications for crypto, for example, will not be enough. You have to go one level further and make sure that you have temper resistance on top. So the aspects of adding maybe some sensors into the design, making sure that they're fault resistant, you can detect, somebody opening the chips, decapping and all of that. You have to think about that when you build your chip. So it's a basis that you need to think through your design and build it in correctly.
I think we're out of time for questions.
Okay, well, thank you very much.
Thank you.